afternoon, ladies and gentlemen. Am I on? Yeah. Let's get started. So we started to embark on some cardiovascular mechanics exercises. The key to these exercises being that you fully embrace the notion that this is a closed system. Okay, so that compartments, if you're going to mess with one compartment somewhere, it's going to have a ripple effect everywhere. Okay, and that if you change one compartment, it will affect the compartment after it, but it will also affect the compartment before it. Okay, so we're going to continue. We worked through this mayhem. It was left ventricular function was decreased by 30%. We're going to work through a couple more examples. We will work through right ventricular function, because it isn't just the opposite of this. Okay, so I want to take you through that to make sure that, or you'll take me through it to make sure that we've got it. Then we're going to do vasoconstriction and vasodilation. I only need to do one because the other will be the exact opposite. So I know you can nail that. There's no tricks there. Okay, and then we'll play a little bit with the pulmonary vasculature and actually just show you why we don't play a little bit with the pulmonary vasculature. Okay, so that's where we're headed hopefully today. This was my piece of paper from yesterday, or from, gosh, I don't even know when we taught last. Maybe a week ago. I'm just going to start with a new piece of paper, just because I want all the space I can get. So we're now going to think about left ventricular function is normal, and right ventricular function is decreased. Okay, so I took you through the first one, and what we're going to notice is as we do these over and over and over and over again, we're just going to be using the same principles over and over and over and over again. Okay? So this is kind of like learning math. We're learning the principles so that it doesn't matter what example gets thrown at you, you can apply those principles and make a pretty good educated guess about what's going to go on. Okay? So let's start with this example. We've got normal left ventricular function, right ventricular function is decreased. So here, right here is our challenge, right? We rarely talk about cardiac output of the right heart, because cardiac output of the left heart is really where all the action is in terms of feeding the entire body. But just like, oh, there's another number dropped there. Just like we saw, I'll put it back up here. Just like we saw when we were in left ventricular function decreased by 30%, we did see cardiac output drop. That was the challenge. Cardiac output of the left heart had dropped. Okay. So indeed, we should fully expect that if we decrease right heart pump function, then cardiac output of the right heart will have dropped. Okay? That's just the challenge. Okay. So, rule of thumb is when we find the challenge, the compartment above and the compartment below are ones that we can absolutely predict what's going to happen. Okay? When we are nearest the challenge, we are best able to predict exactly what's going to happen. So can someone predict what is going to happen based on this problem in the systemic veins or the pulmonary arteries? So you pick your compartment and you tell me why you think it's going to be that way. Okay, so take a quick look at it. Think about what's going to happen in the pulmonary arteries based on that problem. Think about what's going to happen in the systemic veins. Okay? We're just going above and below the problem. So start me off. Yeah. So we're up here? Awesome. Decreased volume, decreased pressure, right? So that's a pretty good one. Awesome. So we start here. You went here next. Perfect. Because the heart, the right heart, what's its job? The job of the right heart is to move volume from the systemic veins and put it in the pulmonary arteries. That's all that pump does. That's all its job is. Okay? So obviously we're filling up the pulmonary arteries less, so we should see less volume, less pressure there. Brilliant. Yeah. Absolutely. So backlog is a good word. We actually, just because if that pump isn't working, we're not removing from that compartment as much as we used to be, right? Perfect. So I would totally buy, you went here next, that we should see an increase in volume and an increase in pressure based on that. Awesome. Okay. So now I'll dictate where we go next. What should we expect? We've just changed this compartment, pulmonary arteries. What effect will that have on pulmonary veins? Changing that compartment moving forward. What do we expect to have happen? And why? Yes. So here, we're talking about this compartment. So you're talking about this decrease in volume and this decrease in pressure because of an end diastolic volume. So that our challenge is cardiac output is dropped, right? And that cardiac output had a direct effect on here. So now we're going to look at the situation right here, right? This decrease in volume, decrease in pressure. How is that compartment now affecting that compartment? So don't take it back to the heart. Go one step forward. Yeah, Simon. Why was that a question, or are you asserting? There you go. Yeah, let's do it. Be assertive. Absolutely, I totally agree. Nice sissy physiologists here today. We want somebody who says, "Damn, Coral, the flow goes down." You're absolutely right. Based on the flow equation, like what is going across the pulmonary system right now, right? It's based on P1 and P2 and a resistance. So we didn't change resistance, but we did indeed drop P1. So we should see flow from the pulmonary arteries to the pulmonary veins to drop, right? Right? So we absolutely should see a decrease in flow from the pulmonary artery compartment to the pulmonary vein compartment. Brilliant. Okay. So I want to set that up. That was, we went here next. Okay? Now I want you to choose where to go. How would you then start to look at this problem? Where are you going to go next? Yes. Yep. Of the left heart? Wait. End diastolic volume of what? Perfect. Okay, so essentially what we've done is decrease in volume and decrease in pressure here, right? This is akin to venous return. This is the veins returning blood back to the heart. Okay, if we've got a decrease in pressure, we are returning less blood back to the heart, and you set a drop in end diastolic volume. Perfect. So let's say, so you went here next. I think you're going to go here next, so let's go 5. And we're going to say because of what happened in the pulmonary veins, we're going to have a decrease in flow into the left ventricle, right? Which means there's going to be a decrease in volume in the left ventricle, right? And you correctly identified that as a decrease in end diastolic volume. Okay? Decrease in end diastolic volume, decrease in stroke volume, decrease in cardiac output. You can't pump what you don't have. Okay? And there it is. There's our drop in cardiac output. Okay? So if we have a drop in cardiac output, what do we expect to see in our systemic arteries? What do we expect to see there? Decreased mean arterial pressure. We've just put out less volume into the pulmonary or into the systemic arteries. We should see decreased volume, decreased pressure there, right? So we went 5, and then we went 6, this compartment. So we should indeed see a decrease in volume and a decrease in pressure here. So you went forward, is essentially was your thinking here, okay? But we can't completely go forward the whole way because compartments affect the ones before it. Okay, so let's think about this for a minute. Right, because the right heart was the problem, have this increase in mean circulatory filling pressure now. How is that going to affect the compartment before it, and why? Any thoughts on that? Yeah. Circulatory filling pressure, yep. Yep. So less flow out of the capillaries. Okay, so that's good. We don't necessarily we're not thinking about the capillaries yet. And the reason we're not thinking about the capillaries is because we don't care what goes through them. At the end of the day, we want to know what's in them. And at the moment, we don't have enough information to know what's in them because we have to know all about what's going in, all about what's going out, right? So flow through, don't really care. But just take one step further back and go, how does this affect flow across the systemic system? Okay? Rather than focusing on what about flow through there, I'm not really caring about that right now. We never cared about flow through. We always just cared about what is in it. Yeah. Right. And that's good. The logic is good. We just cannot focus on the capillaries. Okay, so at the moment, we've never dealt with the capillaries until we've had all our information. Okay? We've never dealt with these until we knew all about in and all about out. Okay? So tell me, same logic, how this compartment is going to affect flow through the systemic system. So the volume coming in, I'm going to argue that we can't really know whether this is for real yet or not. We're still trying to predict this compartment. Okay, I know you can see the numbers, right? But if you didn't have the numbers, we don't quite know what this compartment is yet. Again, I know, yeah, so this is where numbers hurt us a little bit. But I'm going to argue, once we get ourselves into thinking about how this compartment affects this one, then we might not be so clear that volume should go down and pressure should go down in this compartment. Okay, so think about how does the systemic veins affect the compartment before it? Yep. it makes it harder for flow to go there. Brilliant. This is also where people talk about this backlog argument, right? And if you dig this equation as much as I do, we could use this one too. When we're talking about flow from here to here, so all of those arguments are completely valid, all those words are completely valid. I know exactly what you mean if you were to say them to me. On a test, if you were to say those words, I get what you're meaning, right? We're normally flowing in this direction, and suddenly this represents, so this would be P1, this would be P2. Suddenly this represents an increase in P2. It makes it harder for flow to go from the systemic arteries to the veins. Why? P2 went up. Our delta P got less, so flow got less. Our numerator has become less, so flow is less. Okay? Yep. So how can we change? So the question is a really good one, because people get hung up on this all the time. In fact, we've already argued about it today. How come I can make P1 systemic arteries and P2 systemic veins when those capillaries are in there causing resistance? First of all, capillaries don't cause resistance. They're just a tube, right? We did have resistance arterioles in here, right? But we didn't change them. So it's all just a set of tubes. So now there's a constant tube from here to here. And the reason I can change P1 and P2 is because that's where I want to know where flow is going from and going to. I mean, obviously by now, you can see that we just assign P1 and P2 whatever we want, depending on whether we're asking flow going from where to where. Okay? I was asking, how does this compartment affect this compartment? So I was asking, how does the pressure and the volume here affect flow across the system from here to here? So I'm allowed to assign P1 and P2 whatever I like. And again, emphasize this, is because we don't know this compartment yet. I know you can see the numbers, that really sucks. But on an exam or on a test, you would not know these numbers. So you don't, I would argue you don't know yet what mean arterial pressure is going to do. So you don't know what pressure in here is going to change. All right, again, you're talking about flow through here. You want to talk to me about flow through the capillary, and I'm telling you, I don't care. We've never talked about flow through a capillary. We want to know, whenever we talked about a capillary, we wanted to know the volume in, volume out argument. So we would know if volume is in there and what pressure is in there, because flow through a capillary is meaningless. The body's not regulating it. Nothing's happening with flow through. But if we can change pressure, that then gets us into filtration. Okay? So that's where these types of exercises, it's critical to predict your 4 major compartments first. And then you have enough information to think about pressure in the capillary. Yeah. Why don't you know what's happening in the systemic arteries? Because I want you to finish this argument right here, and then we'll go. Let's finish this argument, and then I'll argue with you, okay? Finish this argument for me. How does this compartment, and again, it's because we have the numbers. So what I'm going to say is, take those away, right? Let's take those away. And so far, you have predicted for me that volume, based on this argument, cardiac output going down, right? You would have then predicted, okay, volume should decrease and pressure should decrease. Brilliant. That's what you predicted for me. So now, talk to me about this piece. Talk to me about what's going on here. Yeah. Right. Absolutely. So we've got it. So yeah, I remember where we were. We got to the word backlog. We got to the word, we got to ourselves to here. So then that would be the other comment was it was harder now to get flow from here to here because pressure's higher. All that's expressing the same thing as this equation. okay? It's harder. Why is it harder? Because there's less of a pressure gradient, so less flow is going to go from here to here. If less flow is going, so decrease flow from, how do I write this? Decrease flow from systemic arteries, which means an increase, let's go here, which would result in an increase in volume and an increase in pressure. So, without the numbers, I would argue now you have no idea what's going to happen in that compartment. It just so happens I put the numbers up because I have to prove to you that what I'm arguing is right some of the time. All right, so I give you the numbers. But if you didn't have the numbers, we're going to get stuck in that compartment. We're not going to know, so does mean arterial pressure go up or down? Right? So you have the number in front of you. Obviously, the issue of cardiac output was greater than the issue of the backlog argument. That's what the numbers say, but without the numbers you wouldn't know, would you? And in fact, it doesn't argue that one is negated. This is still happening. This is for real. If the backlog wasn't there, the volume and the pressure in the aorta would actually be way lower, right? But this is impinging on that, increasing the volume and increasing the pressure a little bit. It just so happens that the net gain is lower, right? It's possible that if we let this person be in this heart attack for 8 days, this argument might outweigh this argument. I don't know. I didn't run the program for that long. Okay, so can you see why you can't just assume what was going to happen there because there was another impinging argument? Yeah. Both are happening all the time. It's a sum of the pluses and a sum of the minuses, right? Both are happening all the time. We would totally have to say both were happening, absolutely. Because there's another, yeah, you totally have to say both were happening. Because not saying one is happening means that you don't understand. So let's say you chose not to talk about this. What does that tell me? That tells me that you don't really understand that it's a closed system. And when you mess with one compartment, you mess with the compartment after it and the compartment before it. Okay, so really embracing the notion of a closed system, we got to go around both ways, at least a little bit. Yeah. Yeah, so the argument now would be, because you know the numbers, the argument would be, obviously, the cardiac output of the left heart had a greater impact than the backlog. Both were still effective. One was causing volume to decrease and one is causing volume to increase. They're just not equal. Okay, if they were equal, there'd be no change in this compartment, right? But that's because you have the numbers, right? In any scenario where you're going to have to apply this information, you're never going to have numbers. You're never going to have before and after. If you're an MD trying to predict why someone's mean arterial pressure is the way it is, they're not going to come to you with a list of before and after numbers. You're just going to measure it and going to go, whoa, looks like it's down. Mean arterial pressure is down. Let's check the heart for cardiac output, right? So, or venous pressure for what that is. Okay, so this is just a tap into getting you to really embrace the notion that this is a closed circuit. Okay, but you can see also that we have used all the same arguments that we did in the left ventricle failure scenario. We just keep using the same arguments over and over again. Okay, one more shout out, because this will happen when you're studying with other people. It is because of the way we went through this, we got confused about the systemic artery compartment, right? But if you chose to do this example where you went here and then with no numbers, here and then went this far, this is where you're going to get some confusion. So it all depends on how you choose to do or answer the question, okay? But at the end of the day, no matter how you do it, you will have shown, I totally understand how one compartment affects the ones before it and the ones after it, which is all I'm after with these types of exercises. Okay, so there's multiple answers to these types of scenarios, depending on how you choose to do the question. The one thing that is an absolute is we can always predict what's happening in the compartment before and after the problem. Okay, so these two, number 2 and number 3, there are right answers for that. These two compartments, depends on how you answer the question in terms of where you got yourself to. Okay, so just be open to the fact that there's going to be variability here depending on how you chose to answer the question. Bottom line is you still applied all the same problem solving. Okay? So now once we're here, now we have enough information to calculate what is in the capillary, not flow through it, don't care. Is there an imbalance in the capillary in terms of volume, and is there therefore an imbalance in the pressure? So only once you know this, and you know this, do I have enough information to calculate pressure in the capillary, and fluid flux, and lymph flow. Okay? So I'm not going to do it because we've done it ad nauseum over and over and over again, but let's just set up what this is really telling us, that if we wanted to think about pressure in that capillary, right? And if I do the diagram like it's depicted here, where volume into is dependent on mean arterial pressure and the resistance. Okay, we haven't changed that. Volume out of is mean circulatory filling pressure. Okay? So you would do your volume into out of argument. Indeed, you know the numbers regarding what mean arterial pressure is. So you can go ahead and use that fact that this model at this time predicted this. If you were in a scenario where you didn't know, let's say a test situation, you would just pick one and work with it. It's all good. I can't argue that that's wrong, so it's all good. Okay? So I would absolutely endorse that you take this example all the way to what is fluid flux and what is lymph flow. Okay? Good study material here. All right? All right, let's jump into another one because they're fun. All right, so what do we do today? We've got systemic arterial resistance will decrease. Okay, so this is arterial or vasodilation, or its resistance is increased. So this is arterial or vasoconstriction. All right, good, good. Resistance is set up here in this model. Okay, set up here in this model. So let's just pick one. Let's go ahead and do vasoconstriction since I'm down here. So let's say the challenge is we're going to throw in a vasoconstrictor here. All right. So we throw in vasoconstriction there. How does that affect the compartment before it? And how does that, and again, these are what we're trying to predict. How does that affect the compartment after it? So pick one and tell me why. We got it? No? Yeah. Lovely. All right, so speaking my language, flow Yeah, so we didn't really mess with P, did we? Ooh, what did we do? Oh, dang. So there it is, increased resistance, therefore decreased flow. That's decreased flow out of that compartment, right? So we should fully expect to see, if I've decreased flow out of this compartment, an increase in volume and an increase in pressure here. There it is. Okay, but now what about systemic veins? It's kind of an extension of that argument, isn't it? If I've got a decrease in flow, an increase in resistance in moving volume from here to here, don't I? So based on this argument, it's kind of the same argument. I got a drop in flow. This is where it's supposed to be going, so I should see a decrease in volume and a decrease in pressure there. Oh, increase. Yeah, decreased volume, decrease in pressure. Sorry, I had a minor stroke there. That's supposed to be 3. I don't know what happened there. Okay. So now what do you want to do? Those are the 2 we should nail. No problem. Now what? Where are you going to go? Trying to predict pulmonary artery pressure and pulmonary vein pressure. Yep. Yes. I do. Right atrial pressure. So close. Yep. Yep. Good. So we've got a decrease in venous return. Awesome. So our thinking is in this direction. Perfect. So the prediction for that compartment is, finish it off for me. Dang. Yes, ma'am. Totally buy that. Okay. Good. Now what? Where do you want to go next? Yes. Decrease P1. Yes. Ingrid, so you're taking us over here? All right. So because of the flow equation, let's write it because I haven't seen it for a while. P1 minus P2 over. You talked about dropping P1. Brilliant. So now we've got a decrease in flow across the pulmonary system, which means there's going to be a decrease in volume and a decrease in pressure. Okay, so this is why we have the numbers up. Because that didn't exactly happen in that compartment. That argument is absolutely for real. That is an influence that's happening in this compartment. But those numbers are telling us there's another influence here. Okay? Because we can't always go around in a circle. We've got to back up the other way. So we have to think about how does this compartment affect that one? Okay, so what happened here, Simon? So we argued this for real, and that was a good argument that when we vasoconstricted here, we had a decrease in volume out of the aorta, which meant an increase in volume and an increase in pressure here. And so now I'm saying this must be affecting what's going on up here because our prediction coming this way wasn't exactly what the numbers said, and the numbers are for real. So how does an increase in pressure in the aorta, like what's going on there? Why is cardiac output down? Left heart's fine. Sorry? Because end systolic volume. So I don't know that we know that, because we don't really know what this compartment is yet. We're trying to predict that. So I would argue we kind of don't know how we're filling the heart yet. Afterload, brilliant, huge afterload, right? So we're right back to isovolumetric contraction. Is it longer, taking longer to get the aortic valve open? We're ejecting less volume, okay? Brilliant. So this does represent an increase in afterload, right? Which, for all those reasons I just mentioned, will result in a decrease in cardiac output. Awesome. Decrease in cardiac output. Yeah. An increase in end systolic volume. As part of that argument, no, but you have to talk about the increased afterload, because that's the critical poke here, right? And remember, afterload is the volume and the pressure in the aorta, right? And that is indeed going to affect volume in the ventricle, right? But the afterload's the critical poke. And then the result of that will be, I'm not ejecting as much, right? My aortic valve was open less. So now I do have an increase in end systolic volume, right? Which was a drop in cardiac output. Let's do that. Increase in systolic volume. Ooh, let's make that part of our argument so we're clear. So if the left heart is not pumping it, what does the left heart do? The left heart moves volume from pulmonary veins to systemic arteries, and it's not doing it. Where is the volume? If cardiac output went down, there's got to be volume somewhere. It's got to be up here, right? So because of the drop in cardiac output, we would absolutely argue that we should have an increase in volume and an increase in pressure here. And because we have the numbers, we can see that that change in cardiac output slightly outweighs the decrease in flow argument. Right? They're close, right? But one slightly outweighs the other. Awesome. Okay, now I want you to think about capillary pressure for a minute. Now we have enough information to know whether there is a change in volume in the capillaries and a change in pressure in the capillaries. Okay, I'm not going to completely solve this in terms of fluid flux or that kind of thing. I just need to make you aware of how many influences now we have on volume into and volume out of. So just real quick bit of thinking on our capillary bed volume in, volume out argument. So volume in had to do with mean arterial pressure. Okay, we've been here before. And volume out, mean circulatory filling pressure. But we also increased resistance. Okay, so there's three arguments. There's two arguments for volume in and one argument for volume out. Okay? The one argument for volume in, right, in terms of this one, it would be in terms of mean arterial pressure went up. Right, so if we're thinking about volume into the capillary bed, I've just increased P1, right, so I did that. So we would expect volume into up, volume in up. Brilliant, increased capillary pressure. But we threw in a resistance. That was the whole challenge in the first place, right? So this would predict increase. I better do this one a little more slowly. Increase volume in to and therefore increase volume in, increase pressure. Got it? And then we threw in a resistance, so this argument stems from flow equals P1 minus P2 over an increased resistance. So flow should go down. Flow into should drop because of that. So decrease volume into, decrease volume in, decrease pressure in. Okay, those are our two volume into, two things that are influence volume into. Right, volume out of. What happened? Oh, decrease mean circulatory filling pressure. So volume out of is, since now P1 is in the capillaries and P2 is the mean circulatory filling pressure, just dropped it. Resistance. There's no resistance in terms of coming out of. Increased, we've just increased the numerator, right? So our flow out of will be greater. Therefore, increase volume out of. If I'm increasing my volume out of there, I've got to have a decrease in volume in and a decrease in pressure in. Okay, so two arguments would say pressure in the capillary drops. One argument says pressure in the capillary goes up. The number says it goes up, which drove me crazy for about a month until I realized the programming was wrong. And in fact, the number does drop when you use the appropriate equation. Okay? Take that to fluid flux. Take that to lymph flow. So you can start to see now how it's all connected. Awesome test question. You're in left heart failure, what happens to lymph flow? It's a 1,000-mark question, which I can never ask, but take it all the way there and you're busting out all your skills. So this vasodilation, right, the challenge being right here, is the exact opposite of the one we just argued. So I'm going to leave that with you to give it a go, okay? Knowing also that this is wrong and that capillary pressure will eventually have gone up. Okay? So the last example that I just want to show you, we're not really going to work with it a whole lot, is what's going on in the pulmonary system and why don't we mess with it as much as we do the systemic system. And here's why. Indeed, we had resistance in our model. Oh, look how my numbers dropped. Lord, that's distracting. We also do have resistance up in the pulmonary vasculature. There's resistance arterioles up there. We don't talk about them much, though. And this would be why. This is an example of pulmonary vascular resistance was doubled. So we went in here, we've got some wicked vasoconstriction of the pulmonary arterioles. So vasoconstriction of pulmonary arterioles. All right, so here's our challenge. Vasoconstriction. And as we would predict, we're going to see then above the constriction an increase in volume and an increase in pressure. Okay, we see that. But then when you look elsewhere, like nothing happened. Nothing happened. Okay? That's because this system is so different across that capillary bed. Okay, so even if you doubled resistance up here, nothing happens because the system offers so little resistance in the first place. Okay, so there are arterioles up there, but they are wicked different from systemic arterioles. So this is why we don't play up there, because they don't affect the system very much. This is why the body doesn't plug into, with the sympathetic nervous system, a whole lot of nerves going in to cause vasoconstriction up here, because it doesn't change the system. Ultimately, it can't, okay, because I need to think about this for a moment. We have 5.5 liters of cardiac output, okay? 5.5 liters of cardiac output across the systemic system goes to 600 vascular beds. That 5.5 liters gets returned back to the heart and goes over 1. We have 1 vascular bed, the pulmonary system, handling 5.5 liters per minute. That's like 8 bottles of wine. 5.5 liters a minute. I need you to think about that number. It's here. Has to handle 5.5 liters per minute. So this vascular bed and this system above the right heart and the left heart has to be wildly different. It has to have no resistance in order to handle 5.5 liters per minute across 1 vascular bed, okay? So while we do set the system up in terms of having pulmonary arteries and pulmonary veins, systemic arteries, systemic veins, we do not mess with the pulmonary system. Okay? Because it is wildly different. It's just so much bigger. Okay? 5.5 liters for 1 vascular bed versus 5.5 liters for 600. Okay? It just has to be wildly different. So there's no power here. When you play with this, you see, there's no power in that maneuver. So the body isn't even built that way. We will never say what happens with pulmonary vasoconstriction, because the body isn't even built to do that, to have that as an effective tool. It's not a tool. Why? It doesn't change anything. So why even be plugged in that way? Okay? So we're not even built that way. Huge, I mean, vasoconstriction of the systemic arterioles, bam, look what we did. That's a mess. So huge amount of power here, right? No power here. So that's why we don't play here. We're not even built that way. Okay, we're done. Have a great weekend, guys.